Okay, good afternoon, everybody. Welcome to the webinar. Let me know if you see the slides. Okay, Nunzio, do you see the PowerPoint?
Yes, I see it. Yes, and I can hear you.
Okay, perfect. So welcome to the webinar supported by ISMIC and Glogolan. This webinar is on the basic concepts in soil hydrology and will be done by Professor Nunzio Romano and by myself. I am Paolo Masta. Basically, this is a 3-day webinar. It will be recorded today, Friday 20 and Monday 23 of February at the same time. So from 1 p.m. to about 5 in Central European time. So basically Berlin or Rome time. As you can see, nobody has the microphone or video because we expect more participants to join our webinar. So you can post your question into the dedicated question icon, and I can moderate the questions, especially for Nunzio that will lead the first day and the second day of this webinar. Just a couple of slides to introduce myself and Nunzio. So I am Paolo Nasta. I work at the University of Napoli at the Department of Agricultural Sciences, hosted by the Royal Palace in Portici, which is a town near Napoli. I got my master degree in 2005 at the University of Torino, which is in the northwest part of Italy. And I got my thesis followed by Professor Ferraris and Romano himself. And then I moved to Napoli to spend my 3 years PhD at the University of Napoli under the supervision of Nunzio. And then I spent 4 years in the United States, first at UC Davis, where I met Jan Opmans, Jirka Simonek, and Jasper Frucht from 2009 to 2011. And then I got another postdoc for 2 years at the University of Lincoln, Nebraska, under the supervision of John Gates and Vitaly Zlotnik. And then I came back to Italy, a sort of a round trip, where I got my position as a researcher and then recently as an associate professor at the University of Napoli. So I have to thank Nunzio as he supervised my master thesis, my PhD life, and most of my academic career. So basically, Nunzio is a bit older than me. He's a senior professor. He has a master degree in civil engineering that he got here in Napoli with a major in hydraulics, and he got his PhD here in Portici in hydraulic engineering. Then since 2002 he's been a full professor here at the Department of Agricultural Sciences in Portici, and for the full he spent also some time abroad at the University of Lansing in the US and at UC Davis also in collaboration with Professor Jan Opmans. His expertise spans ranges over different spatial scales. So he leads the laboratory of hydrology here in Portici for the direct determination of the soil physical, chemical, and hydraulic properties. Then he leads also our hydrological observatory in southern Italy. Is located in Campania. which is also kind of a synthesis between hydrological observatory and open air laboratory, where we have, then we will describe more in details, we have a sensor network into experimental areas, and we are carrying out different research activities by using different sensor and experimental techniques. And of course, we also work at the catchment scale and regional scale. So Nunzio has also expertise in mapping soil vulnerability and resilience indicators at catchment and regional scales. And we are working recently on the most important indicators, I think, from a hydrological point of view, which are, for instance, the water storage in the Vado zone, the transit time, especially related to groundwater or root water uptake transit time, soil organic carbon stock, and also many other indicators. So the outline of this webinar, as I said, it is organized in 3 days. Nunzio will lead mostly the first 2 days, because we will introduce the importance of the soil physical properties and the soil water content in the first day. Then in the second day, the day after tomorrow on Friday, he will talk about the soil water potential, its definition and measurement methods. And then he will finish by presenting the soil water dynamics, so describing the Darcy's equation, Richard's equation, and the fundamental soil hydraulic properties, which are the water retention function and the hydraulic conductivity function. On day 3, I will take the lead. So I will introduce the importance of water balance in the soil vegetation atmosphere continuum. And then we will use Hydrus 1D to simulate water flow and solute transport. So we will organize an exercise by using Excel and Hydrus 1D to simulate water flow and nitrate transport across a layered soil profile. Okay, now in the first part, I will be presenting the definition of soil, the soil properties, and let's say the importance of the solid phase into the soil. And then Nunzio will take the lead to present the liquid phase, so the importance of the liquid phase in soil hydrology, and so on, as outlined in the presentation. So basically, the soil, if we look at the Earth, on the planet Earth, we see that the layers are very thick. So if we start from the inside, from the inner core up to the mantle, so we see that they are very thick layers, and under a geological point of view, it's very, I mean, this is very important for that point of view. But if you see the crust, also the crust is a kind of thick, if we see it as a pedologist, but the soil is a very thin outer layer of the planet Earth. So it can be only 1 meter deep or even less. So it's the outer skin of the Earth, and it's so important because it covers the planet's land surface, and it connects the atmosphere, the hydrosphere, the biosphere, and the lithosphere. So it's very important because it's where rock meet life. And so it's very important also because the hydrological cycle happens especially in this very thin situation. Under a pedological point of view, we can split the soil profile into layers or horizons, which commonly are referred to the following sequence. So we can have the O horizon, which is made of undecomposed litter with fresh and decaying organic matter. So it's characterized by high porosity, low density, because there are like plant tissues such as leaves, twigs, and there is a lot of biological activity going on. Then there is the A horizon that welcomes the roots and is made of mineral soil mixed with humus and organic matter. And this soil tends to alluviate downward by erosion and accumulate in the B horizon, which is the zone of illuviation. Basically, it's the accumulation zone where the clay and the iron oxides accumulate across time. Then there is the parent material, the C layer, which is the unconsolidated sediment, the weathered rock, and there is little biological activity. Roots can reach this layer, especially in semi-arid or arid environments. Finally, there is the bedrock, which is the R layer, which is made of unweathered base rock. So this kind of pedological view of the soil profile, we will see that in the end, does not necessarily correspond to the hydrological functional system. Because we will see that the soil profile can be split into functional layers that behave differently to move water into the system. So the soil is basically a three-phase system made of solid particles, of course. There is the liquid phase, occupied especially by water, so which is the main liquid occurring into the Vado zone. And then there is the gaseous phase occupied by soil air. And then we can already present the volume mass relationships into the soil, because these three phases interact by them. So basically the solid phase occupies most of the volume of a soil sample. And then water and air play together depending on the saturation, desaturation processes. So we have the first relationship is made up by particle density, which is the dry mass over the dry volume. As indicated, you can see the symbols on the left. So you can refer to MS and VS as the solid mass over solid volume. Usually, this measurement is very difficult to carry out. So we basically refer to a benchmark value, which is an average value that corresponds to 2.665 gram over cubic centimeters. On the other hand, we have bulk density, which is called officially the oven-dry bulk density, which is the solid mass referred to the dry mass over the total volume of the soil sample. And you can see the photos on the right part of the slide, and shows the oven and a scale. So it's very easy to measure directly the bulk density, because you just have to go to the field, collect your soil sample with a metal cylinder, take the soil sample into the lab, put it in the oven at 105 Celsius degrees for at least 24 hours, 24 48 hours. So basically a couple of days. And then you have to weigh on the scale the dry mass, and then we calculate the bulk density, which is one of the first fundamental properties, soil properties, that characterize our system. Then from the bulk density, it is possible to calculate soil porosity, which is another very, very important soil property, which basically is the volume of pores, so the volumes occupied by water and air divided by the total volume of the soil. And on the right, you can see the simplified equation, which is 1 minus bulk density over particle density. Okay. And finally, we have also the void ratio, which is also another very important property that can be used in other situations, which relates again the volume of the pores divided by the volume of the solid mass. And these relationships can be used in different situations. And typical values of bulk density range around 1 or let's say 1 gram over cubic centimeter. So you can see in the table, the units are referred to kilogram over cubic meters. And so you can see that a clay soil in the first row, you can see 1,100 more or less, with the corresponding porosity of almost 60%. And this is very, very important, because this kind of bulk density value is related to high porosity. In contrast, if you see the last row, you can see, for instance, a loose soil made up of kind of spheres that can have a close packing, and so they can have a high bulk density and corresponding low porosity. So high bulk density can reach up to almost 2,000 kilograms per cubic meters, and the corresponding porosity can reach up almost 0.25 porosity. So basically, I'm going to talk about very, very quickly about the solid phase, because we want to focus mainly on the liquid phase that Professor Romano is going to present after this very fast presentation. There are like two main important features of the solid phase. These properties are said to be static or intrinsic, because they don't change over time, but they do not depend on other external factors, but they are intrinsic into the soil and characterize the soil. So one of these is the soil texture, and the second one will be the soil structure. The soil texture is defined as the relative proportion between sand, silt, and clay. As you can see on the left in black, you can see, for instance, the classification of the USDA association. And so you can see that the sand is distinguished by silt and clay according to specific ranges in millimeters. So the sand, for instance, can be represented by the yellow circle, more or less spherical, let's say, which spans between 0.05 millimeters and 2 millimeters. And clay are the very tiny little particles. So you can see the black dot that is below 0.002 millimeters. Of course, in our lab, we measure particle size distribution. So I mentioned about the open dry bulk density. Now we can focus on also on the particle size distribution as a proxy of soil texture. And in our lab specifically, we combine two methods, the sedimentation method to estimate mostly the silt and clay particles, combined to the sieving method to estimate the most important classes of sand that range between the fine sand and the coarse sand. And so you can see the measurement points. Usually in our lab, we estimate 11 points that can be fitted, optimized by a particle size distribution equation. So there are many equations available in the literature, and we can choose different equations according to the number of points. Of course, more equations that are based on a few parameters probably are more are better in this case when fitting 11 points, but there are also multi-parametric equations like the Fredholm, for instance, that can be very efficient at cost of using a high number of parameters. So you can see here an example of a soil texture triangle according to the USDA classification. So there are like 12 textural classes. And so the laboratory measurements will place our soil type into one of these 12 classes according to the percent of sand, silt, and clay. Finally, this is the final slide for the solid phase, showing the importance of soil structure, which is made, the soil is made of aggregates, or called beds. So the basic solid particles are arranged and organized in macro aggregates that, of course, are different in shape, size, and orientation, and produce different porous channels where water flow will occur. And of course, there are like many categories of soil structure. As you can see, the single grain, so typical of a loose soil, like the desert dust, or can be massive, meaning tightly packed, or aggregated, which is an intermediate situation made up of particles organized in different clods. And so you can see different classifications. Of course, these kind of pictures, which are old-fashioned as well, show an idea of the aggregation of solid particles. And so you can see six different situations where the water flow occurs. Of course, there is also the importance of macro porosity, preferential flow, which is very, very difficult to simulate. So we won't, of course, we won't go into the preferential flow problem, because this kind of webinar is basic and is addressed especially to master students and PhD students. But we want to remind also that in reality, under real world conditions, there is the impact of preferential flow that merits specific webinars or specific discussions. Okay, so this was my last slide. I propose just 5 minutes of break, just in order that I can control the situation and if everything is fine into the webinar in Teams. And then Nunzio will start the discussion on the liquid phase and the importance of soil water content. Okay, see you into 5 minutes, let's say.
Do you think, Paolo, I start with my...
Yes, Nunzio. Yes.
Okay. Paolo, let me know when you see the
Yes,
screen.
we can see the screen and hear you very well.
Okay. First of all, welcome everybody to this seminar. And I would also like to thank Paolo for this nice introduction. Okay, I will talk just a bit about the saltwater content, and start with the classic definitions. First of all, we have the gravimetric water content. That means usually it's the Greek symbol theta, theta m or W, is the ratio between the mass of water over the mass of the solid, only solid. So this means that at the numerator we have the mass of the wet soil minus the mass of the oven dry soil over the oven dry soil. We try also to make some every time we can to make some very short exercise, and here you can see an example how if you weight the soil sample, a wet weight of 150 grams, and then you put in the oven, and then I'll try to reply also to a question about the oven dry weight, and the balance says 108 grams. Then you can see it's relatively easy just to make the computation, and we have a gravimetric water content of about 39%, 0.39 or 39%. That means a kilogram of water on a kilogram of dry soil. Actually, this definition is very useful and in chemistry, but in soil hydrology, we prefer to refer to the entire volume that we consider in our modeling tools. So we prefer to refer to the volumetric water content. This is very important. This is the definition that we usually use when we talk about saltwater content. Saltwater content means, in most of the case, the volumetric water content. The definition is here, is the volume of water on the volume of the total volume of the soil. As Paolo mentioned in his introduction, is the total volume is the volume of the particle, the volume of the water, and the volume of the air, the pores occupied by the gaseous phase. And in the international system of units, we have the cubic meter of water on a cubic meter of dry soil. Usually in practical situation, we use the centimeter, the cubic centimeter of water on cubic centimeter of dry. It is what is important is to have, of course, a consistent units. So if you use centimeter, use centimeter. If you use meter. But the units should be consistent in your computations. But now I try to respond to a question that I read in the Q&A box. And the question is about the identification of the dry soil, but what we consider as the dry soil. This is a really important and I will address this issue when we talk about the measurement of water content. Okay, and there is, of course, a relationship between the gravimetric water content and the volumetric water content. And you can see in this slide this relationship. And so you usually what you do, especially in the lab, you measure the gravimetric water content. So if you multiply for the ratio of the bulk particle density, the bulk particle density is the ratio of the mass of the only solid on the total volume, and divided by the density of water, the mass of water or the volume of only water. This is the relationship. So you can move from the gravimetric water content to the volumetric water content. And this slide is, I think, is something that we can discuss, because you can read in the papers. Sometimes people use soil water content, but you usually find even the term soil moisture. So what is the difference? So try also to discuss about what we read in scientific papers. So, and this is not so easy, and the term soil moisture does not have a single shared meaning, and depends even on the scientist background, and depends on the different disciplines. And I also try to clarify the point in my paper in Journal of Hydrology. But also a very nice point was made by Sonia Seneviratne in the Earth and System review. Well, from the practical point of view, we can consider the soil water content in a point, just a very small volume of our system, and you measure the content of water in this volume. Soil moisture depends on how large is the volume where you are considering the soil water content. For example, just if you look at this slide, the volume A is very relevant for people dealing with remote sensing, because they are interested in the amount of water in the uppermost part of the soil profile. So the soil moisture is a sort of the average of soil water content in the first 5 centimeter, 10 centimeter. I don't want that you all agree on that, but it's just to make things clear or more understandable when you see soil water content or soil moisture. And again, in this picture, you see the volume B. The volume B, for example, is of interest for the agronomist or for people that are interested in the entire amount of soil water stored in the rooting zone, for example. So again, is an average of the different soil water content that you have in the entire soil profile. So the meaning of soil moisture also means sometimes have the concept of averaging different soil water content. Soil water content change in different parts of the soil profile. So I don't want to be exhaustive on that point, but just to let you know that there was a discussion about the difference about soil water content and soil moisture, and this is a way just to talk each other and to understand what's going on even in the next of these seminars. Okay, I'm sure that Paolo is collecting many questions, and on that point. So why we are interested in saltwater content? We are interested because it's a variable that is a state variable. You know, in physics, state variable means that give us an idea of the status of the system. So it's important not only in agriculture and hydrology, but also in meteorology, in hydraulic engineering and soil mechanics. Soil mechanics, especially during the next decades, the landslides and that make a lot of progress considering the unsaturated flow. But saltwater content is also very important for the movement of nutrients in the rooting zone and gas exchange in the system. And again, also now more than in the past, saltwater characterization and measurement. Saltwater content is important for precision agriculture, for optimally for set up optimal irrigation strategies and sustainable water resources. Now we are very interested in sustainable land and water resources. So after the definition, just move to the most important measurement techniques. We can split these in mostly two main categories: the direct methods and indirect methods. And of course, as the word says, the direct methods also imply the collection of soil samples and to use these and to quantify the saltwater content. You can do this directly in the field, but mostly you do this in the lab. The indirect methods measure not, as you can imagine, directly the soil water content, but measure a physical or physical-chemical property that is strongly linked to the soil water content. And so this is why most of the time you have to use a calibration to move from this physical-chemical property to the soil water content. So let's just talk a bit about the direct method. The direct method actually is just one, is the so-called thermogravimetric method. Thermogravimetric because you mostly weight the soil core, and then you use the oven to have the dry soil. So we have to collect the soil core, the undisturbed soil core, and then we will discuss about it. And then you weight with a precision balance. You weight this core. So you have the weight of the soil, but you also weight the tear. For example, the steel cylinder that you use to collect the soil core. Then after that, you put this in the oven at 105 degrees centigrade for at least 24 hours. It depends. So now I try to respond to that point, but then after this you weight again the soil core, and then you have the dry weight, and below you see the formula to obtain the gravimetric water content. So 2 points. First point is the definition of a dry soil, as I also see in the Q&A box. Well, it's relatively simple. this is an agreement. An agreement of the International Soil Science Society. Why? Because, of course, first of all, especially in soil hydrology, we are not interested in the water that is strongly linked to the soil particles or in the clay, in the small part of the clay particles. Why in soil hydrology we are not interested in this? Because we are interested in the movement of water, the movement of water in the soil, vegetation, atmosphere system. So we are interested in what we call the free water. And many years ago, many decades ago, many laboratories was involved to find the right temperature where the free water evaporates. And they collect all this information, and for most soils, different kind of soil textures, and they realize that this free water just evaporate in a range between 100 centigrade and 110 centigrade. So, and it could be strange, 105 is just the mean value between 100 and 110. So this is the magic thing about this funny number 105. Again, 105 is just the average between 100 and 110 centigrade. So this is an agreement. This is an international agreement. So why we need an agreement? Because we have to compare. We need a common basis to compare the data that we collect. The other point is the time that soil core remain in the oven. You can see here just a schematic is 24 hours. It's a sort of a lower threshold. But it depends on the type of soil. Basically depends on soil texture. So you can have 24 hours for sandy soil, but if you have a clay soil that the binding of water to the particles is higher, you may need even more than 36 hours. But the residence time of soil core into the oven, of course, depends on the type of the oven. If you have a static oven, okay, you need some more residence time. If you have a ventilated oven, then you can reduce this residence time. Anyhow, I suggest not to go lower than 24 hours. 24, 30 hours is okay. But again, you can just put the soil core out of the oven, just wait and then put it again in the oven, and then you make a measurement after a couple of hours. And if you realize that there is no change in the weight, okay, you can assume that you have a steady situation. So, and everything seems so easy, eh? Very easy. You collect the samples, you weigh in a balance, and then you put in the oven, even in the oven that you have in your home. But what is the bottleneck of this method? What is the key situation that make this measurement not so easy? So the bottleneck is the collecting of the undisturbed soil cores. And every one of you, I am quite sure, every one of you that try to collect a soil core, you can realize that if you are dealing with a sandy soil in the uppermost part of the soil is relatively easy. In 10, 15 minutes, you can collect this. But if you have a heavy clay soil, and it's the time to collect the undisturbed soil core is much higher, 30 minutes or even 45 minutes, because here you see in this slide how we collect the undisturbed soil cores. We need to open a pit, and then we put the steel cylinders, and then we move the cylinders, usually in duplicates, so to have an average situation, and then we put the cylinder into the soil by hand with a hammer very slowly, and then we also move the as long as the cylinder move down into the soil, we eliminate the soil around the soil core, the cylinder, just to reduce or eliminate the friction around the core. This is really important, because if you insert the core into the soil and you don't eliminate the soil around, this friction just make the soil disturbed. So just to have a less disturbed, undisturbed is just an ideal point. But if you would like to have a less disturbed soil, the practice to eliminate, to scarify the soil around the steel cylinder is very important. Then you move slowly, a couple of centimeter by couple of centimeter, and then you remove the soil around the cylinder. So this gives you an idea the time required to collect the undisturbed soil core. And again, it's important to obtain the undisturbed soil core if you need the volumetric water content, because you need a precise information about the volume. So this is why, because if you collect disturbed soil, you only can obtain the gravimetric water content. But if you are interested in the volumetric water content, you need to know quite precisely the amount, the volume where this soil is contained. So this is why one bottleneck of this method is the requirement to collect the undisturbed soil core. Of course, there is also another limitation of the thermogravimetric method. First of all, I have to say this is a sort of a standard, and is a sort of the thermogravimetric method is usually employed to have a reference for calibration. For example, if you want to calibrate the indirect methods, so the thermogravimetric method provide you with a very accurate and precise value of the salt water content in the soil core. Paolo, I'm sure you are collecting many questions on this, but most of the time, I want to stress this point, most of the time people, even land managers, stakeholders, think that it's very easy to measure to collect the soil, put in the oven. It's a very simple technique, but it is not, because you have to spend time, you have to use skilled people to collect the undisturbed soil cores. And of course, you can use different kind of cylinders. You can use this kind of cylinders that we use, for example, in our even to calibrate some indirect methods, and you have these transparent PVC cylinders, and this also is an interesting way to collect the undisturbed soil cores because you can see the layering. Yeah, and Paolo in his introduction also give you an idea about the soil layering and the importance to characterize the different layers. And this is again another way to collect the undisturbed soil cores. Again, you can see where we do this by hand and we use the hammer. The advantage is also that this kind of equipment can help obtain the soil core even at greater soil depth, even 50 centimeter, 1 meter below the soil surface. And then we also can collect larger soil cores using this kind of equipment that is a percussion equipment that obtain soil core of about 60 centimeter, even 1 meter. And again, this is also very useful if you want to collect this core and to see the layering of the soil core, and then you can cut the plastic cylinder, and then you can test in the lab the different parts. Okay, and after the direct method, we move to the indirect methods. As I said before, we use this indirect method to overcome another limitation of the direct method. The other limitation of the direct method is that you cannot make again the measurement in the same point, in the same location. Why? Because you have extracted the soil core, so you cannot replicate the measurement in the same point. So one advantage of the indirect methods is just you use a technique that you can replicate. You can get measurement of soil water content in the same location. What is the other the reverse of the coin? The reverse of the coin is that you need a calibration technique to move from the information on the variable that you actually measure to the soil water content. And of course, any calibration technique induce some errors. So I have listed here the main indirect methods. The gamma ray attenuation, I just put this as an historical, but usually you do this only in the lab, but there are nuclear techniques that the gamma ray now is not, as far as I know, not used any longer. But then we have the frequency domain reflectometry and capacitance probes, the time domain reflectometry that I'm quite sure most of you knows. I will talk just a bit about the active neutron probe, but the only reasons I talk about the active neutron probe is to introduce what I call the passive neutron probe that maybe you knows more, is the cosmic ray neutron probe. Okay, and the resistive probe. So these are very very cost-effective. They very cheap sensors that the principle of functioning is very basic, because you have a sort of electrical resistance. So there is an electronic circuit, that there is a current that move in this two rods probe, very, very small. And of course, the electrical resistance depends on the amount of water, because if the water content is high, the system is more conductive, so and less resistive. On the other hand, if the soil becomes drier and drier, the electrical conductivity is low, and this means that the resistance increase. You can buy these even on Amazon, and it's very cheap, about 10 euros or 20 euros for each probe. But the very easy, you can put these in the plant in your balcony at your home, but the accuracy and the precision is relatively low. Just to give you an average of the amount of water. Even what I can see, this kind of sensor give you a rough idea, from my point of view, of course, only if the soil is wetter or is drier, but is not very. This kind of sensor is not very useful for if you want to quantify the amount of water into the soil system and the soil water content. So this kind of probe is useful if you want to have a rough idea if the soil is relatively wet, or if the soil is becoming drier and drier, so you need to watering your plant. But most of the modern indirect sensors are based on the measurement of the dielectric permittivity. So then we will have a small break, but I want to just spend some time on this property. This is very important to understand how the modern indirect method work. And this is, I think, is also very important to understand and to exchange some ideas on the dielectric permittivity, so you can appreciate more, I hope, the difference between among the different probes that the market sell you or propose you, because the functioning, even though they measure the dielectric permittivity, the way they obtain the dielectric permittivity is relatively different. Okay, so let's consider as Paolo said in his introduction, soil in a very schematic way is a porous material composed by three main components: the solid phase, usually for a medium soil texture 50%. Then there is water, 35%, for example, and the other part, the other pores are filled by the air, usually at atmospheric pressure. Of course, the volume occupied by the soil particle remain quite the same if the soil does not swell or shrink. Of course, we are not considering a swelling soil or shrinking soil. Just in my talk. But of course, shrinking and swelling are also very important processes that affect the measurement of soil water content. But this is not the point now. Then we have the porous system that can be occupied by water or air, depending if the soil is wetter or depending if the soil is drier, so more void pores or more water pores. Dielectric permittivity is a property of any substance when he is subject to an electromagnetic field. And the molecules, because of this electromagnetic field, just start polarization because of this electromagnetic field. And depending on this polarization, there is this property, the epsilon, the Greek symbol epsilon is the relative dielectric permittivity. Now, for air, the relative dielectric permittivity is 1. For the solid particles, minerals, ranges between 3 and 5 on average. But what is interesting that the dielectric permittivity of water is close to 80. So from this situation, people come up with the idea that the dielectric permittivity of soil is mainly governed by the variation of the water contained in the soil. So there was a very important field of research on the measurement of soil dielectric permittivity. Again, sorry for this, but I think it's. I don't think it's very tough, but it's important just to go a little bit into the intimate meaning of the dielectric permittivity, because as I show you later, this is important to understand the differences between the different probes that the market propose you. Well, from the electrical point of view, for most of you that are familiar with the electrical topic, the dielectric permittivity can be considered as a complex relationship. This relationship is component by a real component and an imaginary component. The real component is strongly linked to the resistance of the resistance behavior of the system. The imaginary component is mostly linked to the capacitance, the capacity of the system to accumulate, to store electromagnetic energy. And on your left, you can see the meaning of this. This is for those of you familiar with the electrical engineering, with electrical topic. Usually in this field of research, they split a property in this way. In this equation, we have the permittivity epsilon 0 in farad per meter. And then the sigma dc is the electrical conductivity in direct current. But there is not only the direct current, but the electromagnetic field has a frequency. Can the frequency of this electromagnetic field can vary? So the omega, the Greek symbol omega, just give you the value of the angular frequency of the superimposed electromagnetic field. The frequency is measured in hertz. And what is interesting in the graph on your right, you see in the blue line is the pattern of the real component of the permittivity as the frequency increases. And you can see there is a plateau at the beginning for low frequency, and then there is an abrupt value that goes below around there is a shift, and then again when you approach the 10 to 8 hertz, you have again another plateau. But what is interesting is that the green line is the pattern that the imaginary component follow as the frequency of the field changes. And there is an increase, more or less rapid increase, and then there is a maximum value of the green line, and then again there is a descendant value, and again the approach a sort of a plateau similar to a plateau of the green of the blue line. And I have put in this graph the usual frequency where most of the soil moisture probe work, and we later we will understand why. Paolo, what do you think if we make a 10-minute break?
Yes, Nunzio. Yes, as you want. I don't know if you want to reply quickly to the questions, because the questions were mostly related to the first part.
Which part? Okay, I can reply to some question. Tell me the which questions, and I try. I leave the slides so we can.
Especially on the story of the 105 degrees Celsius. For instance, what adjustments are required for accurate bulk density measurement in soils with high mineral or salt content that may partially evaporate or chemically alter the soil during the standard procedures?
Yeah. No, this is a very good question. So when we have a situation like the guy mentioned, it's not a good practice to collect the soil and move the soil to the lab. Usually the location where you collect the soil is far from your lab. And so one practice, if you cannot do in another way, one practice is just to embed the soil core very strictly in a plastic bag, and to avoid the evaporation as much as possible. Of course, this also depends on the period of the year when you collect the soil core. If you are during summer, of course, the evaporation is enhanced and higher. But if you are in winter, the evaporation, of course, is lower. But so this is something that you can do when you must move the soil core to your lab, especially, and you can see if there are some water evaporating in the plastic bag, you have to measure very accurately even the bag. So just to understand what's going on. The other thing that you can do if you have the salt or again, salt is not, as far as I know, a very real problem, but the evaporation of water can be a problem. You can try to reduce this problem or to avoid this problem, just to make the weighting of the collected soil just in the field. Of course, if you use a precision balance, you have to have a sort of a tend, because even a small wind move can affect the precision of your measurement. So I hope that I reply to this very useful question. Any other question?
Yes, there are other few ones. One is from Sophia. If we want to calculate the bulk density of an undisturbed soil samples in a PVC cores, can we oven dry the samples at a lower temperature during a longer time? Because I think PVC cores into 105 degrees in the oven is a problem. So probably, I don't know why they have to collect soil samples into PVC instead of metal.
No, I can understand. Instead of a metal, PVC is cheaper, Paolo, than to obtain the steel cylinder. Well, it depends on the thickness of the PVC. As far for my experience, if you have a PVC and the thickness of the cylinder is not too small, then well, you can, for 24 hours or 30 hours, you can leave this in the oven. But of course, you can check before making the collection of the undisturbed soil core. You can put in your oven your cylinders, your PVC cylinder, to see if there is some deformation. If you see deformation, okay, this means that is not good. But for my experience, it depends on the thickness of the cylinders. If the thickness is adequate, maybe you can leave this in the oven. But again, you have to check, as always in our measurement, we have to check if leaving the cylinder, your PVC cylinder, in the oven, if this cylinder deformates. I hope I have replied to this interesting question.
Yes, unfortunately, the temperature must be 105, just by convention. And
no. Of course,
because
you
otherwise it would be problematic.
Otherwise, the measurements are not comparable. And
exactly.
This is a standard. This is an international agreement. Otherwise, you cannot compare the measurement. This is the standard. Other questions?
Another couple of small questions. Is the free water also the plant available water? I think he means not the soil water, but the free water. So I think it's not possible.
No, free water is considered the water that is binding in the soil. Not only binding, because as we can see tomorrow on Friday, there is the cohesion and adhesion of water molecule to the soil particles, and depends if the particles is sandy or is clay, but free water means that water that mostly can move relatively easy in the soil pore. This is the general agreement of considered free water, and this is important for soil hydrology. Soil hydrology is interested in the movement of water from soil to the root to the into the vegetation and toward the atmosphere. So this is the basic. There is not a real strict definition of a free water, but mostly I can say water that can move relatively easy into the pore, and then you can compute the water content, the metric potential, and then you move water from one part of the system to another. Okay.
Excellent. Okay, last question before the break. Tang is posting, is the measured hydraulic conductivity still representative if the soil cores are collected horizontally from the walls of the soil profile? For instance, with the sampling ring inserted parallel to the ground surface.
Okay, I understand. This is another nice point that always come up with my students. Of course, why we collect. So the question is why we collect the soil cores horizontally, vertically. I mean, this is because we in soil hydrology, and especially in the soil vegetation system, we are the movement of water is mostly in the vertical direction, and I understand that water then also moves in the horizontal direction. If you think that, so this is a sort of what you want to model, and the volume of your system that you are modeling. If most of the time, as I understood Paolo will show on next Monday, is the 1D, one dimension movement of water in the soil vegetation system, and this is basically most of the water movement in soil hydrology are in one dimension and specifically in the vertical direction. Of course, I understand that there are also the horizontal direction, but if you want, there are even lateral direction. If you think that this information is important for your model, okay, you can collect the soil core horizontally instead of vertically. But again, you should be sure that your model just can account this information, of course. Otherwise, I think this is a waste of time. This is my point. Paolo?
Okay, there was a reply to the PVC. I think because does the soil deformation matters after collection to calculate the bulk density?
Of course, yes, because it affects the entire volume. I remind you that we are interested in the volumetric water content, so the importance to collect the undisturbed soil cores with the cylinder is to have a very precise knowledge of the volume of the soil. Otherwise, this is lose information on the volumetric water content. So it's very important to have very precise information of the total volume in the soil in the core of the cylinder. Otherwise, you make an error in measuring the soil water content. So if this deformation is not comparable with your, so it depends on the position, of course, as always. Most of you, I always warn you to consider the precision. If you are measuring the saltwater content with 3-digit precision, you have to consider that every situation, every measurement should have at least 3 digits of precision. Otherwise, you have to use the rule or the numerical operation to compute the precision of your value. This is another story. This is a story of using the numerical operation with the arithmetics and so on when you use the precision. Okay. Any more?
Okay, I think it's enough. Maybe we can take a break.
Take a break at 10 minutes is fine.
10
So
minutes.
we
Okay.
will adjourn at 2:45. Is okay?
Okay, okay. If
Okay,
there is
see.
no
Objection, of
comments,
course.
I think it's okay. Okay.
Okay. Okay, Paolo, I am quite ready to go on with this presentation. I don't know if
Yes, it's fine.
do you have feedback if people is again in the room? I don't know because I have the presentation.
No other feedbacks so far.
Okay. No, in the sense that they are ready to start.
Yes,
Yes.
yes, I
Okay.
think so.
Okay. I also see in the Q&A that the condition of a dry soil is a key issue. And again, I would like to emphasize that the condition of a dry soil is not a unique condition. This should be clear to everybody. But as always happen, especially in soil physics and soil hydrology, most of the definition rely on agreement, general agreement. And the condition of a dry soil, especially in soil hydrology, is an agreement because we, in this discipline of soil hydrology, we are mostly interested in the amount of water that move from one part of the system to another part of the system, from one soil location to another soil location, from the soil depth to the plant to the leaf and to the atmosphere. So this definition is mostly depending on the what we need, what we want to model, what we are interested in. Of course, especially when we have the clay materials, you cannot let water evaporate at 105 centigrade. The binding of the water molecule in some montmorillonite or illite clay materials is so strong that even if you dry the soil at more than 200 or 250 centigrade, you do not remove the water that is so strictly linked into the clay materials. So again, this definition of a dry soil is a standard definition just to solve most of the practical application. So just to be clear, since I have seen other questions in the Q&A box, but I understand that there are many papers dealing with the issue of the dry soil and the limit of soil water content, the lower limit of soil water content in the soil. Okay, so I move. And we were talking about the real and imaginary component of the dielectric permittivity. I hope that this is not too boring, but I do believe that this graph is very important to understand. For those of you who are interested in to understand more about the differences between the different probes available in the market. So we have the three main different sensors that measure the dielectric permittivity: the capacitance probes, the frequency domain reflectometry, in the literature FDR, or the time domain reflectometry, very well known, the TDR probes. Well, just to understand from the electrical point of view, the difference. The capacitance sensors just act like a capacitor. For those of you who are familiar with the electrical topic, the capacitor is a component of the radio. Now we have the other way, but the capacitor is one of the component together with the resistor. Resistor and capacitor are the component of the radio. But and then we also have other components. But when there is an electrical field, the capacitor has the ability to store electrical energy, and this electrical energy can be measured using the permittivity and linked to the saltwater content, as I said before, because water has very high permittivity. The relative permittivity is 80. Then the frequency, the FDR sensor is also a sort of capacitor. Use the soil as the capacitor, but it works differently because it measures the resonance frequency, the maximum electrical resonance frequency of the electrical circuit, as you can see on your right. And this resonance frequency is linked to the permittivity and again to the soil water content. I think that every one of you knows the TDR. The TDR again measures the apparent electrical permittivity of soil, but what measured is the velocity of the propagation of the electromagnetic signal that move into the probe, the transmission line of the probe. But these are also to give you an idea, and I hope I try to clarify, because many people, when they talk to me, they make a mix up, they confuse the capacitance sensor with the TDR and vice versa. But it's important, and if you spend a bit of time to understand the electrical functioning of this probe, everything, I am sure, can be clearer. Again, the capacitors, when you have at school, the capacitors are just some device that store electrical energy. This is the simplest way I can say to explain this. And the capacitor, you have the electrodes, usually metal, and then there is the dielectric material. What is the question is, what is the dielectric material? In our case, is the soil. And the soil, again, is a very complex dielectric material, because soil is made up by pores, so by air, water that fill the pores, and by solid material. So it's not so easy. But this is the dielectric material. So what we are measuring with the capacitance probes is the dielectric characteristic of this dielectric material, and this is soil. And the term capacitance that you can find in the manuals guide for users is the capacity of this system to accumulate energy in the form of electrical charge. And this is directly linked to the permittivity of the system. So I hope, I don't know, Paolo, are you collecting a lot of of Q&A? But I think these are the basic to understand the capacitance probe. And these are some examples here of capacitance probes that you can find selling in the market. Again, this is the theta probe, and you have a probe body, and there is in the body there is the electrical circuit that produce the electrical circulation of the electrical field, and then there are some pins, the shield rods, the rods that you insert into the soil, and so the soil contained between these rods is what we have called the dielectric material. So measuring the electrical charge that is accumulated in this system when there is an electrical voltage that produced by this probe. So this can be related, measure the permittivity, and then using a calibration procedure, you can obtain a value of the soil water content. And then I will show you later what you can do. Another kind of the capacitance sensor is the hydrosense. The hydrosense again works in a little bit different way of the theta probe, but again you have electronic components that generate an electromagnetic field, and there is the waveguide and embedded in the soil. The soil works as a dielectric material, and this system again measure the dielectric characteristics, so the permittivity, and the permittivity, and then you obtain the soil water content by calibration. And you can see here the hydrosense calibration that you can find even in the literature. Another example of capacitance probe is the eco probe. Again, the principle is always the same, because you put this into the soil. The soil generate when there is the electrical field that move into the system. There is a change in the voltage that the system acquire, and the change in the voltage depends on the amount of water. Again, this is another way to look at the this kind of capacitance probe. What is important is completely different from the TDR. The TDR obtain the dielectric permittivity by measuring how an electromagnetic wave move into the rods. So instead, this capacitance sensor just monitor the change of voltage. And this is from the electrical point of view, this is completely different. And what is the difference? The difference is the precision on your measurement, in the sense that the capacitance sensor, even though in the last decade there has been a huge improvement in this kind of sensor, but the TDR still remain the most accurate and precise indirect measurement of soil water content. So again, just to be clear, now I am presenting the indirect method that are, of course, not the reference like the direct thermogravimetric method, but has the many advantages. The advantage is that you can leave the sensor into the soil and measure continuously or quite continuously the change in soil water content. The disadvantage of this kind of indirect probes is that you need a good calibration to obtain a good value of soil water content. So a good calibration means that it depends on the accuracy that you need for your investigation. I hope this is clear. Everything should be made in depending on the objective of your research, of the objective of your work into the field. Again, I like very much the electrical things. This is why I want to boring you a little bit more on the functioning of the capacitance sensors. And again, you see on your left the classic capacitor that you can find in somewhere. There are two materials, then there is air in between, and there is some negative and positive part of in this electrical circuit. But if you put a dielectric, you have this kind of situation with the positive and negative molecules that move depending on the electrical circuit. And again, the capacitance is the ratio between the charge, the electrical charge that you superimpose in the system, and the voltage. Yeah? So the voltage is superimposed, and then the charge is the charge that the dielectric store the electrical charge. And one of this kind of the latest capacitance sensors put in the market is the Teros 12, for example. I don't want to push, just to give you, this is the same webinar, just to give you an idea of what the market produce. One is show you is the Teros 12 made by the Metal Group. What is interesting of this probe is that you not only measure the dielectric permittivity, so you do not only measure the soil water content, but you can also measure simultaneously the soil temperature and the electrical conductivity. So you have three variables that you simultaneously can measure. But again, the principle of functioning is that these capacitance sensors just generate a charging time of the capacitor, and this charging time, as you can see on your left, bottom on left, you see the variation of the voltage with time, and this curve depending on the dielectric permittivity of the system and the dielectric permittivity of the system. Your system is soil, but the electric permittivity is mainly governed by the amount of water into the soil. This is the main concept. Again, I want to stress this. The system measures the relative dielectric permittivity of the soil, but this dielectric permittivity is mainly governed by the amount of the soil. This is why we can relate this to the soil water content. And I hope this is clear to everybody, but I'm sure that Paolo is collecting some require of clarifications. Again, we have other type, and just only to give you what you can find on internet or in the market, the EcoProbe, Teros 12, and so on. Then move to the frequency domain reflectometry. The FDR sensor, one is the Diviner. The Diviner 2000 is the typical example of frequency domain reflectometry. That means this probe just measure the change in the frequency, in the electrical frequency. So the system is a bit different, not the voltage, but the frequency, the electrical frequency of the radio wave, or some electrical people prefer to call the resonance frequency. What we can do, I see that there are some papers in the literature on the precision and accuracy of the Diviner, and they realize that this is a very good probe, but the installation is should be done very carefully, because the precision of this sensor seems that depends more on the way you have installed this sensor into the soil profile. Apart this limitation, there is the strong advantage that you can put the Diviner into the soil profile, and as you can see in the picture in the center of this slide, you can measure the permittivity, and so the soil water content at a different soil depth from the soil surface. And of course, this is a very big advantage. And again, maybe this advantage can be is a sort of a trade-off. Is a trade-off with the having less precision in the measurement of soil water content. I hope.
Nunzio, sorry,
Yes.
there is a question from AD Daniel. He needs more clarification on the Teros 12. He also asks about on how to couple the Teros 12 with the measurements of electromagnetic induction device, which is a completely different spatial scale, I think.
Yes, okay. So the Teros 12. Okay, let's make a clarification. You can see in this this slide all our capacitance sensors, but on your left, the EcoProbe measure only the soil water content, or better, the electric permittivity, and you obtain the soil water content. For those of you who are more interested in having more information, Teros 12 give simultaneously the information not only on soil water content, but also on the soil temperature and on the electrical conductivity. Why? Of course, Teros 12 is more expensive than the EcoProbe or the other capacitance probe. But I should say that another limitation of the capacitance sensors, the value they measure is affected by the temperature. So in the calibration of this sensors, it's important also to understand the effect of temperature on the measurement of soil water content. And in my lab, we made papers, and maybe Paolo can put the reference in the chat. We made a paper on trying to understand the effect of soil temperature on the measurement of the capacitance probe. So this is why is really important to have the simultaneous information even on temperature. And of course, and I'll show you later why the capacitance sensor, but even the TDR and even the FDR are affected by the salinity content. And this is why another advantage of this probe is to obtain information on the apparent electrical conductivity. So you can also correlate your measurement of soil water content on the amount of salinity that also affect this measurement. So this is why I only would like to give you a sort of panorama on what the market can provide you. Of course, it depends on the amount of money that you have available, because the EcoProbe are cheaper than the Teros 12, but again, it depends on the target of your investigation, the amount of money that you have available to do this research. Again, I would stress once more the importance not only to measure the soil water content, but also to measure the temperature and the salinity, especially if you monitor for days and days, because the fluctuation of the soil water content, this is another point that some researchers overlook. The fluctuation of the soil water content, of course, depends on the diurnal fluctuation of temperature, but these fluctuations are also affected by the negative influence of the soil temperature and the salinity, the electrical conductivity. I don't know, Paolo, if I replied to this very interesting question. So I try to go on. Paolo? Okay, no, I can't hear you. Anyhow, so I move again, as I told you, this is the frequency domain. The frequency domain, again, there is also an electronic circuit, but the principle is a bit different, because this probe measures the resonance frequency. And one advantage is to put this in the soil profile with you use an access tube, and then you put this in the profile, and you obtain the information at the different soil depth. I don't know, Paolo, if I can go on. I can't hear you any longer. Any other questions? Paolo? I miss you. I can't hear you. I hope you hear me. Any feedback? Paolo? Paolo? Okay, you can hear me. Okay, good. Well, maybe you can use the chat if something is not clear. If I try to give some information, but at the same time, this is a basic webinar, so I try to maintain the information in a very basic way. But I try, and I do hope you take advantage of this basic information, even though maybe people sometimes they don't like very much the electrical circuits or the electrical principles. Okay, let's move to the what I'm sure that almost all of you knows very well, the TDR, the time domain reflectometry. And again, from an educational point of view, I am asking you all if you understand from what principle the TDR comes from. And the basic idea is the failure in the underground wire, the electrical wire. Because so the example is very simple. If you have a failure in a water pipeline, you very easy understand when there is the failure because you have water that goes everywhere. But if you have a gas pipeline, again you smell the gas, so you can understand more or less where the failure is located. But the problem is that if you have a mouse that have made a failure in the electrical cable, is difficult, very difficult to understand where the failure is located. So, what to do? If the idea is here. If you launch an electrical wave into the cable, and the wave just get the failure, there is one wave that go on into the system, but there is a return wave, as you can see in this animation. I hope you understand the animation. The vertical black line is the failure into the cable, the electrical cable. And if the cable is, there is an electrical wave into the cable, this wave, part of the wave just goes on into the system, but another part is reflected. And since we know the velocity of this wave, reflected wave, the only things that we have to compute is the distance. And this is a way that even today, people that have to check the failure in the electrical cable just is the way to find the location of the failure into the electrical cable. I hope you have get this information. And so the time domain reflectometry, the theory of the time domain reflectometry is that we consider the velocity of propagating wave, of a transverse from definition is a transverse electromagnetic wave, TEM. So this is conveyed in a transmission line, and the roads are embedded into the soil. So the equation that govern this velocity is in the bottom right of this slide. The Vt, the velocity of the transverse wave, depends on the speed of light, and this is a constant, the speed of light in the vacuum, and then over the denominator is the square root of the relative magnetic permeability, and the apparent, again, you see the apparent dielectric permittivity of the medium. Who is the medium? What is the medium? Is the soil. The soil with the soil particles, with water and air, but basically what is important and what is governed by the electrical permittivity is the amount of water. And again, if this is the probe has, in this case, 3 rods, and the L is the length of each rod. And from the equation of the velocity of the transverse wave, you can compute the apparent electrical permittivity, and then the velocity is just the definition of velocity is the space divided the time. So the delta t is the travel time, the time that the wave takes from the beginning of the road to the end, and then to return to the system. So this is why you can see at the denominator the constant 2L. Why? So people sometimes ask me, but why 2L? My students always ask me, why 2L? 2L because we are considering the wave that starts from the top. You can see from the top of the probe that you see on your right, and then the wave reach the bottom, and then, as I show you before, this wave just return and then move in the opposite direction. So this is why the wave just move 2 times from top to bottom, from the bottom to the top. So this is why in this formula you see the constant 2L. I hope this is clear. And then you can see the people, especially the people dealing with the electrical engineering, just make a lot of fantasy on producing different kind of probes, but because you have a different kind of the electrical field, and it's important just to confine the electrical field, so to have the best, the optimal measurement. But the typical TDR probes that we use are the bifilar probe. You see here the electrical field that is produced around the 2 rods, but another, and we use this very often, is the trifilar probe. Trifilar probe, you see how the electrical field change around the probes, around the rods, and so you can understand how this affect the measurement. Again, this bifilar probe or the trifilar probe. Hope this is also clear and affect the precision of the measurement. Again, it is important every time that you keep in mind the importance to define not only the measurement, but as Paolo said in the introduction, I am an engineer, so of course I am interested in the value or the measured value, but it is from my point of view, and hope for even from you, is important to quantify the uncertainty associated with your measurement. You always have to try to quantify the uncertainty and to transfer not only the information on the average value of any variable, in this case the saltwater content, but you also have to transfer. This is my message. This is my message. It's very important to transfer to the end users, to professionals, to land managers, not only the average value, but try to quantify as the best way possible, quantify the uncertainty associated with your variables, to quantify the uncertainty associated with the maps that you produce. Hope things at this point is a key point, especially today, and especially with the tools that we do have today to quantify in the best way we can the uncertainty always associated, because we are talking about measurement, and measurement are always affected by measurement errors. So it's important to, again, to quantify the uncertainty. And in this slide, you can see different kind of cable tester, the quite old Tektronix 1550C that we still have in our lab, but we also have a couple of TDR 100 with the only disadvantage that the TDR 100 does not have the screen, but the screen is very important. Why is very important? Because we need to look at the how the voltage change, because the measurement with the TDR, and I want to be very clear on that point. TDR does not measure the saltwater content. Actually, TDR measure the permittivity, but actually you obtain the permittivity because you look at the waveform. The waveform is important. And this is the waveform, what you see on the screen. This is really important because you have a coaxial cable that make the electrical wave moving. Then this transversal wave get the in this slide, the trifilar probe, and then there is the epoxy handle that maintain the three rods, and you see the 0.1 when the wave enter into the probe, and then when exiting the epoxy handle, there is a disturbance. Of course, there is a disturbance. This is why the reflection of the wave change from 0.1. You can see the black circle in the up left of this slide, and then there is a disturbance and get the point 2. And then at point 2, the waves move into the roads and get the point 3. Point 3 is there is what I have called before the failure. There is no way for the wave to move into the metallic in the metallic road. So this is why the wave, just a part of the wave remain into the system, but get back from 3 to 2. So what we measure is the distance between point 2 and point 3 into the screen. You can see again in the top left of this slide, you can see what we measure is the distance in centimeter, but the time is the same from point 2 and point 3. So this is why I say that what the TDR measure is this wave form and not just a value on a screen. So this is why again it's important to acquire the waveform. And I show you an animation provided by Paolo Castiglione, was a PhD student in my department, and you can see the generator, the pulse generator just generate the waveform move in the coaxial and then go back and then goes to the screen, to the sampling oscilloscope. What you see, what you see in the screen, on the screen, is what you have in the top right. You have this black disc that move, and you obtain this waveform. Again, I show you the animation made by Paolo Castiglione. So again, there is the TDR. In the TDR, you have a pulse generator, and then you also have the oscilloscope, the sampling oscilloscope. Then the pulse generation, what do the generator? The generator just create a square wave, a square electrical wave that move into the 50 ohm coaxial cable, then go into the probe and then back to the oscilloscope. What you see on the oscilloscope is on your right. The reflection, the screen is the reflection and the time. You see the movement. And this is again, I want to stress all of you that what is important is to obtain the waveform. And then from the waveform, you obtain the apparent permittivity, and there is a sort of calibration curve, general calibration curve for most soils, and that works quite well for many soils, especially if you are interested not in the absolute saltwater content, but if you are interested in the changes of saltwater content, because in the changes the errors most of the time eliminates. If you are interested to have a very precise saltwater content, then you have to collect the soils and then to make a local calibration. But for most of the practical application, you can use this quite general apparent calibration curve that relate the apparent dielectric permittivity to the saltwater content. Paolo, I don't know if you are with us again, because
Yes, Nunzio, I came back. I was out for a couple of minutes.
Okay. I thought we have lost you. We miss you. Okay. I don't know if there are question. The topic is a bit maybe can be tough for somebody, but I hope I was clear. But if something was not clear, please let me know, and I'm trying to reply in the best way I can.
Actually, there is one question from Shoaib on quantifying uncertainty, because you referred to
Okay.
uncertainty.
Yes.
He said, are you referring to statistics? Do you have a particular method? Do you suggest? Maybe a relevant paper where this is applied will be helpful.
Okay, of course, the uncertainty is a statistical means a statistical issue. There are many techniques. There are some very simple techniques. The easiest way to quantify uncertainty is to make many measurements. If you want to measure the I don't know some distance, you use a certain technique, and you make the technique is called the repeated measurement. You make 10 measurement, 20 measurement, 30 measurement, 50 measurement of a certain distance, and then you try to quantify. It's difficult that you always have the same value. It depends on the tool that you use, but you have an average. If you put all these measurements together, you have an average, the mean value, and then you have the minimum and maximum value. So the minimum and maximum value give you an idea of the uncertainty. So the interval between the minimum and maximum value give you an idea of the uncertainty. But this is the main difference between analogic equipment and digital equipment. The main advantage of the digital equipment, the electronic equipment, do you know what is the advantage? Is that they not only make 20, 30, 50 measurement, they make 100, 5,000, 10,000 measurement. So you can obtain with more confidence, and be careful. Confidence is has a statistical meaning. So if you have 1,000, 10,000, 50,000 measurement, you are more confident. You have an average value, mean value, and the you can quantify the confidence interval. So what means that you have many data, 100, 1,000, you have the probability distribution of this information, of this data, and then you can, from the probability distribution, usually is a normal distribution, the statistical normal distribution, and you can compute the mean value and the confidence interval. Usually, in statistics, you can quantify the uncertainty in the 90% confidence intervals or the 95% confidence intervals. Unfortunately, I cannot go into this, but to my students, I dedicate a couple of lessons to the question of the measurement errors and how to quantify these errors. And of course, you have to consider that if you are not satisfied with a certain technique and you would like to have a greater precision, then you have to change your tools. And again, it's also very important to when we talk. I'm sorry, we are talking about different things, but I think it's important. It's important to make a distinction between accuracy and precision. Why? Because it depends on the measurement errors. Accuracy means that the bias is relatively low. Your measurement is accurate is if the bias is low. Do you want to have an example of a bias? Is if your watch just have a bias of 5 minutes. And now they are 10 o'clock, but your watch just look at 10, 5 past 10. So this is a bias. It's a systematic error. Precision means that your measurement has very low random errors. Why? Because the measurement errors divide in 3 categories. The first category is the very gross errors, but we don't care about this. The other 2 errors are very important, are the bias and the random error, systematic errors and random errors. So the idea is to have as low as possible the random errors, means to have a good precision. But anyhow, it's important to quantify the random errors in terms of average and confidence intervals. I don't know if sorry, maybe other people are not interested in this, but it's very important when we talk about measurement to talk about measurement errors.
Thank you, Nunzio. There are other 2 interesting questions on calibration, so you are in the right slide. First question is, would the amount of soil samples used for calibrating the water content to the dielectric permittivity depend on the spatial scale of interest?
Oh, actually, but so again, the calibration process, if you want to use the calibration equation that you see in this slide, okay, you have to take this as it is. So, but if you make your own calibration, of course, you have to make the measurement more times and try to quantify the coefficient, for example, of this polynomial equation, and to quantify not only the average value that you see here, but also the uncertainty in each of these coefficients. And this is the point on the calibration. The number of samples, okay, depends. If I understood well, the question depends on the extent of your study area. So if you are working in the same soil type from the pedological, physical point of view, okay, you can collect the samples in a couple of points just to have the particle size distribution, the bulk density, the oven dry bulk density, to see if things are quite similar to you can make the calibration only in a couple of locations. But if your study area is quite large and you need to use the TDR in differently textured soils, then you have to repeat this in the different part of your area. That's it. I don't know, Paolo, if I replied to this question.
Yes. So basically, I want to complement there are like several options to use. So you can use the top equations as showed in the slide, or you can use the factory equation given by meter, for instance, for the Teros 12, or you can use your own calibration equation if you collect several soil samples for the thermogravimetric, for the direct measurements of soil water content, which is the benchmark measurements. And so you can relate the benchmark soil water content to the dielectric property and build your own calibration function. Consider that there are like impacts of temperature, electrical conductivity, so on the permittivity water content calibration. So this is another debate, very interesting discussion on that, and there is still room to progress on the on this topic, on the calibration of sensors in general. So this is very, very interesting, and also I think this question is very, very interesting related to the spatial scale. So how many soil samples do we have to sample if the spatial scale is different or the soil is not similar? So this is still open to my opinion and open to debate. And so this is a never-ending story, I think, and we need much progress. But Nunzio, I have probably the last question on the calibration by Pietro. Is there a standard procedure to produce a good calibration curve? How should we proceed for direct versus indirect methods?
Actually, I don't know. Calibration process, from my point of view, is a sort of art, and you have to accommodate the procedure considering different constraint. Constraint does not mean, from my point of view, limitation. Constraints depends on the experience and expertise of the people that make the calibration. And as I said before, the expertise also involve some knowledge of the measurement errors. I think it's really important to quantify the uncertainty in the coefficient E0, E1, E2, E3. And you can see the graph that the picture that you can see on your right, taken by the original paper by Top. You can see that there is a quantification of the uncertainty. The dashed lines that you can see in this plot give you an idea of the errors that you have in when using different kind of soils. Soil is a very complex, porous material. So I don't think that there is a general rule. For example, we are very careful in our lab when we deal with clay materials, clay soils, because clay soils are always very tough, porous materials to deal with, comparing to sandy or loamy sandy soils. So again, maybe especially when you are in the lab, to collect in the optimal way, the best way as possible, the undisturbed soil core that you use for the thermogravimetric method. Why? Because the direct method give you the reference. So if you make a large error in the reference, it's difficult that you can obtain a good calibration process, a good calibration polynomial equation. So again, depends on the type of the equipment that you have in your lab. Do you have a good oven, or do you have a very simple oven? Do you have a ventilated oven or a static oven? Do you have a very good and expensive, of course, oven that is insulated by the rest of the room? So, and do you have can you control that the temperature in the oven remain at 105 centigrade all the time? So these are the questions that you have to ask to and to respond to quantify in the best way as possible the uncertainty associated with your calibration process. I hope I have replied to I have answered to this question.
Okay. Yes, if they have any other questions, they can keep posting. So Nunz is defending himself very well.
Okay. Or at least defending my experience. This kind of webinar, from my point of view, I am very happy. Is just to transfer my experience and expertise to you all, and this is the only spirit that animate my participation in this webinar. Well, let's continue. Using the TDR in the field, and again you can see how important it is for us to use the TDR 100, but this is without the screen, but we need to look at the wave. The waveform is very important. Why? Because only the pattern of the waveform give us an idea if we are doing a good measurement. So the idea is to look at the waveform. So this is why, again, TDR requires skilled people. So when the operator like the wave, he stores the waves. So the measurement of the TDR is not a value, is not 0.3, but the measurement is the waveform. And this is what we did in our lab. We put everything in a backpack. Then there is the TDR operator, and he put the sensor into the soil, and he looks at the waveform, and only if the operator likes the waveform, he stores the waveform. Then going back after the hard day work in the field, back in the lab, and he download all the waveform, analyze the waveform, and obtain the permittivity, and then using the calibration, the universal calibration, the top calibration, or the local calibration, you obtain the salt water content. I hope that this is very important to transfer to you the experience that Paolo and I had with the TDR. Just we want to be clear. The TDR measurement is not that you put the probe in the soil and then read 0.35. This is not. The TDR is something completely different. The TDR measurement means to collect the waveform and to analyze the waveform. I want to be very clear on that. Hope that everything is clear on that point. So another classical question that I have from my students, but even from people that cannot very easily understand the differences between the TDR and the capacitance sensors. And again, I put in this slide again the equation of the permittivity, the real component, the imaginary component. But don't worry if this is too complicated. But just to make things clear, we have the plot showing the permittivity versus the frequency of the electromagnetic field, and we have the pattern of the real component and the pattern of the imaginary component. I remind you, the real component is linked more to the resistance of the system, the resistivity, and the imaginary component is linked more to the capacitance, the capacity of the system to store the electrical field. So after this, you can see that the pattern depends on the frequency changes from 1000 to megahertz or gigahertz. And there are the interfacial polarization of the molecule, dipolar, and so on. I don't want to go into detail on this, but what I show you is the question is, at which frequency the capacitance probe work? This is the question, and this is the answer. Most of the capacitance sensors work at frequency of the electrical field that ranges from 70 to 100 megahertz. What we see that the real component in this vertical line reach a sort of a plateau, but this is not the case for the imaginary part, epsilon with the 2. Comparing to the TDR, the working frequency of the TDR ranges between 0.5 to 2 gigahertz, and is the you can see the sort of reddish bars I put into the plot. And what you see that the reddish vertical bars are contained in the zones of the plot where both the real component and the imaginary component are a sort of a plateau, a steady. What does it mean? That we really are measuring the a sort of unique value of the electric permittivity. So this is why I hope that this slide give you an idea not only of the difference between TDR and a capacitance probe, but the fact that the TDR is an equipment that produces a little bit more precise value of the permittivity and hence of the salt water content. I don't want to say that the capacitance are not good. No, this is only again to just going a little bit into detail of the functioning principle of the two probes, just to give you an idea of the difference between these two sensors, and of course the TDR is more expensive than the capacitance sensor. But I hope just going a little bit into the detail of the dielectric permittivity of the transversal wave, just in a very I hope in a very relatively simple way, just to give you an idea why the TDR probe is a bit more precise than capacitance sensors. And again, this only a plot that show how the measurement is affected by the frequency, the functioning frequency of the sensors. But as Paolo mentioned it before, there is the temperature effect and there is also the salinity effect. Besides, the TDR is also mostly used to quantify the solute concentration in a soil. So because the real component give us information about soil content, but the imaginary component give us information and quantification of the solute concentration, salt concentration, for example, into the soil. Any question on this? Because I move on the neutron probe, Paolo.
So far, no questions on that, unless they post it immediately. I don't know.
Okay.
But so far, no.
They are completely stored. Astonished.
Still 1 hour, but please push Annunzio. Be aggressive. Post questions.
Okay. I try to stimulate question, but I understand that something is so new for some people that and they have to digest this all these things. Okay. I don't want to go into detail of the neutron probe, the active neutron probe, but it's important from the educational point of view. This is a webinar on basic soil hydrology, and this is why I do believe that from the educational point of view, it's important to understand the passive neutron probe, to understand how the active neutron probe, neutron sensor, just works. There was used a lot 20 or 30 years ago when I was in US, in Michigan, working with Joe Ritchie at the Michigan State University. I worked a lot with the active neutron probe. Very easy. I show you that there is a probe that you put in an access tube, and there is the atom of beryllium that produce fast neutron that impact against the hydrogen in the water around the probe. And because of this impact, the fast neutron become a slow neutron, as you can see in the bottom right of this slide. The physicists call this phenomenon the thermalization. Thermalization means that the fast neutron become slow neutron, and slow neutron are detected by another substance and produce a count of the slow neutron. And this counting is related to the amount of hydrogen in so the amount of water into the soil. So this is only just to give you the idea of the principle of functioning. And this is the neutron probe in the field, and we made the counting of the neutron probe. Of course, this is also there are some nuclear risk when using this, because the emission is there are some radiation. When I was in US, always I have some detector just to see the amount of radiation, and that I got Anyhow, of course, even this method requires a calibration, and again, the only thing is to collect again and again the undisturbed soil cores. And you can see here, this picture just try to answer a couple of questions that we received today, just to collect using the steel cylinders for undisturbed soil cores, just to have a quantification of the average soil water content, but also to have an idea of the uncertainty of our measurement. So I hope that these two pictures give an idea of the quantification of the uncertainty when you make a measurement, even for calibration purposes. And then many years ago, we use different of this. We put the access tubes in different parts of the plot. We have the neutron probe that move from one side to another, and it's important just to make to point out that the collision of the fast neutron to the slow to produce the collision against the hydrogen and the producing slow neutron depends on how the soil is wet. So the volume, the measurement volume in when the wet soil is a sphere of about 15-20 centimeter, but in the case of when the soil becomes drier and drier, this the measuring volume enlarge, because you need more collision against the water molecule, and these measuring volume is so the volume where you can obtain the average saltwater content is enlarged. There is a sphere of about 40-50 centimeter, or even an ellipse with the larger, the greater diameter, or of about 60 centimeter. Well, I don't want to go into more detail on this, but only just to understand the cosmic ray neutron probe. This is what is really an advance in the measurement, but a great advance in terms of soil moisture, in the sense soil moisture, because you have an average information on relatively large areas, and you can understand that you can see here. Then we go more into the detail that why I call this the passive neutron probe. Passive neutron probe because there is no radiation source that produce the fast neutron, but we collect the fast neutron from the cosmic ray that get our planet. What is really interesting and make this very useful, especially when you want to compare the information that you get from a satellite, for example, that you have the average radius of the measurement area is ranges from 15 hectares to even more than 25 hectares. This in the horizontal area. The depth that you investigated by this equipment ranges in the interval between 15 centimeter and 70 centimeter, again like the active neutron probe, depending on the amount of soil moisture. 15 centimeter if the soil is relatively wet, more than 50, 60 centimeter if the soil is relatively dry. Again, so we go into the detail. There is the high energy neutron that collides to the soil particles, and for this collision we have the neutron, even fast neutron, that impact the water molecule, and there occur the thermalization. So the fast neutron becomes low neutron. And the detector, the equipment, just read in a certain way the thermalized neutron, but also the fast neutron that still get the equipment because they get directly the soil particle. From this difference between the fast and the slow neutron, we have an information on the average soil moisture on the area of tens of hectares. And again, some more detailed information. We have fast neutron, the hydrogen atoms into the soil, and the soil can be at relatively low soil moisture or high soil moisture, and the fast and the epithermal neutrons in the air are inversely proportional to the surface soil moisture. Another very nice information is that the fast and the epithermal neutrons are sensitive to change in soil moisture comparing to the thermal neutrons. So all these information help us to measure the average soil moisture in a range of tens of hectares. And there was a very nice paper made by Colley and colleagues in 2015, and then produced information on the larger concentration of neutrons in a certain area. You can see about 200 meters, and the higher concentration give a good correspondence and a good reliability of the measurement. But again, I will start the animation again. You can see even the penetration depth, give you an idea of the average depth where there is the most concentration of the fast and epithermal neutrons. It's about, in this case, 52 centimeter below the soil surface. So again, from this information, is important to understand that the soil depth, the vertical information, the depth of the measuring volume for the soil moisture depends on how the amount of water into the soil. In the sense that for wet soil, this thin layer is about 15-20 centimeter, but if the soil becomes drier, the volume of soil investigated by and the average soil moisture is the average depth for measuring soil moisture is more than 50, 60, even 75 centimeter. So this gives us an idea. This is also a very important information because we need to associate the measuring volume. Always we need to know when we measure soil water content the extent of the volume where we measure the amount of water. So soil moisture in this case for the cosmic ray neutron probe is on average an area of about 15 hectares, and the depth depends on how wet is the soil, the 10-15 centimeter for relatively wet soil, but more than 50-60 centimeter for relatively dry soils. There are some progress, of course, very fast progress with the cosmic ray neutron probe. This is something developed at Jülich in Germany. They put the cosmic ray neutron probe on a minivan, on a rover, and they move in a certain area, and in this way they have collected information on areas ranging from 10 to 50 kilometers in a map at the soil moisture in about 1 day. So it's really amazing, and and it's also interesting to see when some scientific group starting from one point then try to make evolution of a certain technique. Now it's important also to understand we are approaching the end of my talk, so it's important. I would like to stress that is really important when measuring soil moisture to understand how important is the integration of different equipment. You can see here this interesting picture. We have in the x-axis the extent, the distance, and then the time. So you can see the different boxes. You have the TDR equipment, and then we have the sensor network. Very briefly we will show you something about the sensor network, but the electrical resistivity induction and the electrical magnetic induction, mobile TDR, mobile cosmic ray, and then how to integrate this more local information with the satellite information or equipment and sensors mounted on drones or on aircraft. So you can it's important when you design your investigation, even try to I do suggest that it's really very successful if one have the possibility to integrate different kind of measuring technique for soil moisture. In this picture, we have shown this graph is time versus distance, but in this slide you can see how the different measuring methods integrate when you have the horizontal axis with the vertical, the soil depth. And you can see here the TDR or the frequency domain reflectometry FDR or the capacitance probe, that you have a very small horizontal spatial scale with a small vertical scale, but you can enlarge this if you use the wireless sensor that I show you later on, very soon. Then, so using this, you can enlarge the horizontal and vertical scale, but then you can integrate this with the geophysical survey, the electrical resistivity tomography, for example, that just enlarge the horizontal scale and the vertical scale of a measurement. Then you can also use the cosmic ray neutron probe, cosmic ray neutron sensors. You can see again, you integrate a point scale, local scale, and field scale, and then of course you have the other sensors. Just a few words on the wireless sensor network. It's very easy now. The cost of this equipment are relatively low. You have these sensors put in the ground, and then they are all connected. And then there is the gateway sensor that collect all this information, and you are on your desk in your room at university, and you look what's going on in the from the different sensors. This is very useful. You can see in the top center of this slide the different position of the sensors. This is the sensor units. You have for example, the TEROS or GS3, MPS6. They measure the soil water content, and we will see next time on Friday the water potential, and we can put this. The antenna into the soil, but even outside, if you don't want to lose the signal. And again, is important. What is important, you can put the sensor at different soil depth. And then there is the coordinator unit that collect all the information from the different location and send all this via GSM. These are pictures of our installation of the wireless sensor network, the SoilNet, into one of our experimental catchment, the Monteforte catchment, MFC2 area is the catchment is the yellow. The yellow line is the drainage divide, and these are way we put the soil moisture sensor, the water potential sensor at different depth into a pit, and everything is connected to the antenna, and we prefer to put the antenna outside the soil, so to be sure that the signal is very well transferred. And you can see the different way to install this sensor network. And here you show all the information, and the experimental field, of course, is has the weather station. So we have the rainfall, the daily rainfall, and then we can, from the temperature, we compute the potential evapotranspiration daily. And in the two plots below, we have the green line give you each so water content measured by each sensor, and then the black line is the average water content in the entire catchment. Then you are wondering what are the black squares. The black squares are the TDR measurement that we use as a sort of to control that everything is working in well, but just to see what's going on. And you see that there are some small line close to each square that give us the information about the uncertainty, is the confidence interval. We quantify the uncertainty. You can see in the second panel the soil moisture at 15 centimeter below soil surface, and the third panel show you the water content at 30 centimeter below. And maybe you are wondering about the cosmic ray. And this is the cosmic ray. The blue line gives you the average soil moisture measured by the cosmic ray. So you can see when the soil is relatively wet, there is a very, very good correspondence with the panel at 15 centimeter. Of course, the largest discrepancies occur when the soil becomes drier and drier. But of course, when the soil is drier, we have seen that the measuring value is changed dramatically, and so things are less easy to understand. But anyhow, the fluctuation of the water content is very similar, and this is very good to have information about the evolution of how soil water content vary during the different period. We are here show 4 years of measurement. Of course, there are some failure even in the TDR, but anyhow, when the advantage to have continuous measurement is that you can get the fluctuation, and this is especially important for Mediterranean areas because the seasonality of the climate, not climate change, but the seasonality of climate is typical of a Mediterranean climate. It is important to catch this seasonality and to make some scenarios on that. And this is my last slide, just to we made a blog information on the observatory of the Alento Hydrological Observatory, and you can access this. We also won the 2020 best blog post on the information about this observatory that belonged to the Terino Hydrological Observatory in Europe. And now we have more than close to 11 years of data collected in different catchments that are different because of land use, different in terms of soil, but they are equipped in the equivalent way with the same wireless sensor network, with the cosmic ray, with the weather station, and so on. Okay, well, I hope you enjoyed this, and now, Paolo, the floor is yours.
Yes, there is one question. Are the fast and thermalized neutrons counts both detected by the detector?
You mean in the
cosmic ray neutron probe?
Yes. And the detector just make a sort of a difference. It's not easy, but difference. So it's a quite different comparing to the active neutron probe. Okay, the active neutron probe just detect the thermalized neutron. This is the functioning of the active neutron probe. The passive neutron probe need to detect both from the difference between the fast epithermal neutron and the thermalized neutron, give you an idea of the average soil moisture in a relatively large area of hectares. Hope this is okay.
And another question from Izari: what explains the breaks in the soil moisture measurements of the cosmic ray neutron probes between 15 April 2009 and 15 August 2009?
Oh, Paolo, this is your. This is up to you. This is up to you.
Basically, sometimes we miss the data for malfunctioning, and we have so many problems in the field. For instance, we have to replace the batteries in the sensor units. So we have to go. I mean, the maintenance of these networks is challenging. So it's
photovoltaic panel, even the photovoltaic.
Yeah,
panel,
even the photovoltaic panels. And there are like the animals. There are the wasps, the wasps in the weather station in the in the pluviometer, and the wild pigs excavating the pits in in the sensors. So we have so many problems. So sometimes we miss data, unfortunately. But sensor networks.
Sorry, Paolo, if I interrupt you. The period seems too large, but because the failure was so big that we need to buy again some equipment or the panel, the photovoltaic panel. So this means that for certain period the cosmic ray didn't work.
Yes, so all these kind of issues happen unfortunately, and but the newest equipment is smarter and smarter. So I'm quite sure that there will be even logistical improvements in the future. For instance,
less failures.
Yeah, less failures. So unfortunately, when you lead this kind of instrumentations, unfortunately, you have a lot of problems, any kind of problems that you can imagine. So that's why you miss some, you have gaps, data gaps.
Another important point that even though everything is controlled electronically and you have all the data on your PC in your room, you need to go to the field at least 2 or 3 times per month. You cannot leave the equipment alone for more than 15 days or 3 weeks. Otherwise, you only at the end, you realize that you you lost everything. So even though you are using a very sophisticated and comprehensive soil moisture equipment, wireless sensors, cosmic ray, they are all connected using the GSM with your computer, but you need to go to the field to check that everything is running smoothly. So sorry, Paolo, if I jump in this.
Yes, absolutely. So that's the point. And by miracle, during the COVID time, there was no issue. So that's a paradox. Before the COVID, there were like some issues, but during the COVID, it was all okay. Oh, maybe there is a new. Thanks for your explanation. So based on that experience, what would you recommend in terms of instrumentations of a soil moisture measurement network? What kind of equipment do you recommend based on your experience?
Okay, thanks for this question that gives me the opportunity to stress one important thing. The important thing is that, from my point of view, from my experience, there is no general rule. The first thing that you have to do is to understand your target, to know your target, and try to make in the best way as possible or in the optimal way possible to design your investigation. So again, my suggestion is to consider, first of all, to have an integration of measurement equipment. One thing is that to have a local measurement and to have, for example, the capacitance probe to connect the capacitance probes in a wireless system and try, of course, accounting for the money that you have available to cover different part of your study area. Again, it's important to have a preliminary knowledge of your area in terms of different soils. Are soils quite uniform or is different in terms of physical-chemical properties? Particle size distribution, bulk density, we will see soil water retention and conductivity functions. So if part of your area are different, you have to put sensors in the different part and at least to have a number of statistical location, the number of locations that are they have a statistical meaning to obtain the average and to quantify the uncertainty. So this is one point, and then usually maybe you can involve some other scientists, people, for example, that they have experience and expertise in geophysical survey for example, the electrical resistivity tomography. That is very useful to give again an information on larger dimensions, even in the lower part of the soil profile. Why we are also interested in the, as Paolo will show on Monday, we are interested in the what's going on deep in the soil, because deep in the soil, this is the lower boundary condition. When you run an hydrological model, you need the upper boundary condition, but you also need the lower boundary condition. The upper boundary condition can be relatively easy to obtain because you have the rain gauge, you have the weather station, so you can compute the rainfall, you compute the evapotranspiration, and so on. But the lower boundary condition below the routing zone, below the 1 meter, 2 meter is difficult. What do you have? We have a bedrock or you have a free drainage? It's different. And the geophysical survey can help you to identify the best way as possible the lower boundary condition. Not only this, the geophysical survey without opening pits and spend a huge amount of money give you also an important information. How your area, the layering, how many layers, the heterogeneity of your system. This is also information, important information when you want to run a model in a certain area. So depending on the first thing is the knowledge of the area, the basic knowledge. The other important thing from my point of view is the target. What is the final aim of your investigation? Otherwise, you spend a huge amount of money and then you don't get what you need. Okay, this is my recipe. Paolo, it's up to you.
Yes, no, I fully agree with Nunzio. We hope that we answer all the questions. So there are no more questions so far. So if you have any other questions, please post. Otherwise, we can close. If you don't have any other questions, because it's 4:40 p.m. at least here in Europe, and so I think it is okay. So just some clarification. So I'm gonna share the slides and the videos because I recorded this video. So we're gonna share the slides and the videos of the 3 days. And the next appointment is Friday, the day after tomorrow. So Friday 20, with the stoichiometric potential and water flux into the soil. So it will be much worse than today in terms of harsh. So it will be another solid class for the participants. And so you can post your questions also on Friday. Okay.
Okay. Thank you, Paolo. Thank you to all of you. Thank you for the
Okay.
questions.
Thank you, Nunzio. Bye
Okay.
bye.
Bye. Bye, guys.